Hello everyone. Today we are going to discuss about network analysis and synthesis. This course is for the third semester. Myself, Dr. K. Hussain. So I am the course coordinator for the network analysis and synthesis course. Before going in detail about network analysis and synthesis, first we will discuss about prerequisite of this course. That is basic electrical engineering. You can say basics of electrical engineering. Okay, so in this we'll review about basic concept, electrical quantities and their units, circuit elements, and also basic circuit laws. Okay, so what do you mean by an electrical circuit? In electrical engineering, we are usually interested in transferring energy or communicating signals one point to other. To do this, we often require an interconnection of electrical component. So based on this is the definition, simply saying it is an electrical circuit is an interconnection of electrical components. Typical circuit or electrical components that we will see in this. So we can say here batteries or sources, voltage source or current source. Different types of elements, we can say resistor, capacitor, switches, transistor, diodes, amplifiers. So all, if you are connecting all the elements, so that is called an electrical circuit. Okay. As per the Merriam-Webster dictionary, the definition it is the complete path of an electric current, including usually the source of electric energy. Similar way, if you are taking according to Encyclopedia Britannica, so electric path, so you can say electric circuit is nothing but path that transmits electric current. You can observe here, so this is the battery, one load, you can say here it is a lamp or anything you can take, which one it takes load. You can take motor or you can electronic components or something. And another one is connecting wires. You can say from battery to lamp, lamp to battery. Okay. So a circuit, electric circuit includes a battery or generator that gives energy to the charged particles, device so that use currents, such as those are the loads, you can say lamps, motors or electronic components, and connecting wires. Okay. Circuits can be classified according to the type of current they carry. So you can say different types of current, already we know that. So AC and DC, alternating current and direct current. Or according to the whether the current remains series connection or parallel connection. How these are divided. Based on that also we can. So two basic laws that describes performance of electrical circuits. So are Ohm's law and Kirchhoff's circuit laws. You can say KVL and KCL. Okay. Now we'll take the review of those. So just now already we have discussed about electric circuit. It consists of three components. One is the source of energy. We can say that is a battery. Either first figure or second figure, if you observe that one, it is a source of energy. Example, it is a battery. Second one is a closed path. Those are the wires, connecting wires. This one as well as this one. And third one is a device which uses the energy. Which one it is? You can say it is like a lamp, load, any device you can see. Sometimes you can take motor, sometimes lamp, sometimes even resistor, whatever you are taking those things. Suppose any connection, if it is open, for example any pair from 1 to 2 or 2 to 3 or 3 to 1. if any part of the circuit is open, the device will not work. Okay, so that is a electrical circuit. It should be closed path. Next, system of units. We know we have many units we are using in our electrical. Okay, but if you know few, that is a basically you can say 7 units. If you know 7 units, remaining all units are derived from these 7 units only. Okay, so those are the base units of international standards. The international system of units, also known as metric system, uses 7 mutually independent base units. Okay, those are here I'm saying. So in that length, you know that length. So name of that is a generally we are representing in units meters. Symbol it is m. Mass kilograms. So symbol is kilogram kg. Time, so seconds. So yes, you are showing for the symbol. Electric current, that is a ampere, unit of that. So symbol is A, capital A. Remaining three, thermodynamic temperature, kelvins. So capital K, it is a symbol for temperature. Amount of substance, any substance you can say molecules. So that is a mole, MOL. So intensity, luminous intensity, that is the name of that unit is candela, CD, it is the symbol for that. So based on these 7 units, remaining all units we can derive. Okay, these are the base units of SI system, you can say. Okay, now SI prefixes. We have many prefixes here. We can say factors. Sometimes generally we are using mega, giga, all we know that. But majority whatever we are showing in the box, those are generally we are using in our circuits. We can say circuits are different subjects, also different electrical circuits. Also we are using these symbols. That is, you can say SI prefixes. Particularly here in this left hand side box, from here K to T, you can say kilo 10 power 3, mega 10 power 6, giga 10 power 9, tera 10 power 3. Generally used symbols. K small k, M capital M, giga, G capital G. And right side in the box, generally we are using that decimal. So small values only can observe here. These are the capital up to T, mega, giga and T. But here 10 power minus 1, 10 power minus 2, 10 power minus 3, 10 power minus 6, 10 power minus 9 and 10 power minus 12. So these are the generally used factors. You can say deci, centi 10 power minus 2, milli 10 power minus 3, micro 10 power minus 6, 10 power minus 9, nano 10 power minus 12, peak. So these are the commonly used SI prefixes. And now we are going for review of basic circuit concept. The first one it is electric charge. It is the basis for describing all electrical phenomena. We know that charge. What is charge? An electric property of atomic properties, particles, of which matter consists. Okay, it is measured in coulombs because a French scientist, Charles Augustin de Coulomb, has found this one. He has invented. That's the reason the name unit has given. It is a coulomb for charge. Okay. Inside an atom, there is a negative charge on electrons, positive charge on protons, and no charge on neutrons. Already we know that the charge of an electron is equal to charge of proton, and that value is E equal to 1.602 times 10 power minus 19 coulombs. That is the charge. How many electrons here? So if you are taking just reverse of that, we'll get that one. So that is 1 C of charge, that is nothing but 1 over that value of 1.602 into 10 power minus 19. So 6.24 into 10 power 18 electrons. This many electrons are there for 1 coulomb of charge. In the laboratories, generally we are using these values. Those are the fractional values of coulombs. That is a pico, nano, micro or milli coulombs. Okay. So laws of conservation of charge. Everybody knows about that. We can't create, right? So charge neither be created nor destroyed, but only transferred. This is the law in classical physics basically, and rarely we can say here. In all cases, it may not be true, but generally, majority of the cases, this is the only law of conservation of energy. Charge neither be created nor be destroyed, only transfers. Okay. Electrical effects are attributed to both separation of charges and charges in motion. So, and also we know that materials, conductor. What is a conductor? It is a material in which charges can move to neighboring atoms with relative ease. That means easily can move from one to another. That means current is flowing in out in general. Okay. One measure of this relative ease of charge movement is electric resistance of the material. Okay. Examples you can say all the metals and carbons. Majority you can say except one or two. So remaining all metals and carbons. In metals, only charged particles that can move are electrons. Okay. In all the flow of electrons, that means it is a charge. Insulators, another material is insulator. It is also material that opposes the charge movement. Ideally, infinite opposition, that is nothing but more charge movement. We know insulators, you can say example dry air, glass, wood, and this type of insulator materials. Another classification of materials is semiconductors. Generally, the properties of semiconductor is in between conductor and insulator. Okay. So examples we can say here silicon, silicon with some added impurity, even germanium. Okay. So these are the semiconductors. Conductors, insulator, and semiconductors are material classification. Okay. Now we'll go for the basic, that is a purely electrical components. We can use electrical units, current, voltage, and these things we'll discuss now. What is the current? Electric current. Sometimes you can charges in motion. So current is net flow of charge across any cross section of conductor. It is measured in amperes because Henri Ampere, a French mathematician and also physicist, so he has given the current he identified. Before that actually, so he has done, that is a invented, is a scientist, American scientist and inventor. Originally he has done current, but he found that current is only due to the movement of positive charges. But he observed that and the net flow of charge across any cross section of the conductor. So the current is rate of change of charge. You can say here I is nothing but the ratio of charge to the time. Okay, I equal to dq by dt. So what is that? Q, you know already, it is a charge. So coulombs per second, right? Okay. In reality, in metallic conductors, current is due to the movement of electrons. However, we follow the universally accepted convention that current is in the direction of positive charge movement. In this figure you can see here, so this one it is a battery in this positive movement. So in this way we are showing here. But actually electrons movement is in this direction. This is negative symbol, this is the electron movement. Okay, we can show here the current, two ways of showing the same current. If you are showing here, it is a 5 amps, right? Is a, for example, if you are taking, it is a plus 5 amps. If you are taking in this way, it is a negative 5. Both are same only. Okay, same current we are showing. In this way, it is a one direction, it is a positive, another direction, it is a negative. So we have two types of currents. Okay, one is DC current, direct current, another one is AC current. DC current, it is a current that remains constant with the time. It won't change with respect to time. It is a fixed value. So figure A shows that, so DC value, it is a constant value without the value of time. Another current is AC current. So AC current, alternating current, is a current that varies with respect to the time. We can observe here, right hand side, that is a figure B. It is a sinusoidal wave, right? So here it varies with respect to time. If time is varying, for example 0, this value is 0. When time is increasing 0 to 1, so this one also it is increasing, amplitude also varying. Again it is decreasing. Okay? It varies sinusoidally with respect to time. So that is the alternating current. All homes we are taking this one on. Generally we are using this current, AC current only. Okay. Next element is that is a voltage. Voltage, sometimes it is also called electromotive force or potential difference. Okay. It is the energy required to move one unit charge through the circuit element. That is called voltage. It is also called electromotive force, EMF, or potential difference. It is measured in volts because Alexandro Antonio Volta was invented this. That's the reason. So the unit of voltage is volts. So voltage is nothing but rate of energy, you can say, because here how much energy is required to move one unit charge. That's the reason here it is dW by dQ. Okay. So similar like current, already we know currents. We have two types of current. Similarly here voltage also we have AC voltage and DC voltage. Okay. So DC voltage means it is a fixed value with respect to time, and second one AC is with respect to, it varies with respect to time. And voltage, here we need to observe polarities, because in the current you can observe based on the directions, which direction it is, whether it is from A to B or B to A. One way we are showing positive, another way we are showing as a negative. In this case we need to represent symbols, that is a plus and minus signs. So plus and minus signs are used to define voltage polarity. Okay. The assumption is that the potential of terminal with positive polarity is higher than potential of terminal with negative polarity by the amount of voltage drop. Here in this figure we observe this is the load and this is the terminals A and B. This is the positive terminal and this is the negative. So this one, it is a potential difference between A and B. Okay, it is called voltage, right? VAB, from this to this. So this one always positive with respect to this one. So this is the higher value than this one. That's the reason we are taking this one. Okay. So that is voltage polarity. So now you can take few examples. Here also same way. Both the figures represent same voltage. So in the figure A, you can see here in between terminals A and B, that is a 9 volts, plus 9 volts. In the figure B, same terminals but the polarities are changed. That's the reason it's a minus 9 volts. Okay, that is voltage polarity. Now coming to the power, we know this one we are generally finding from the voltage and currents only. How we are finding that? So power is nothing but rate of change of energy. Okay, so that means the rate of change of energy per unit time. It is measured in watts. James Watt, Scottish inventor and mechanical engineer, invented this power. So that's the reason the unit of power is in watts. So that power, it is dW by dt. So just you divide and multiply it by dq. So dW by dq into dq by dt. So already we know that what is dW by dq, that is it is nothing but voltage. dq by dt, rate of change of charge, right? So that is nothing but what? Current. So P equal to product of V and I. Okay, just you can check the units also how it is. So V already we know that is dW by dq. So joules, W, this is the unit joules, and this one it is coulomb. And here coulombs per second, right? So that is just to multiply V into I. V into I, joules by coulombs into coulombs by second. These two cancel, joules by second. Joules by second is nothing but watt. So that is P equal to V. Okay. Even power we can represent in terms of other elements, that is with respect to resistance. Okay, other formulas of power you can see. These formulas generally we are using. So they are simply for derivations of power with the different versions. Okay, P already we know that P equal to V into I, V equal to IR. So just substitute that value in this above expression, P equal to VI, you will get P equal to I square into R. If you are taking same Ohm's law, I equal to V by R, right? So just substitute here, you will get P equal to V square by R. Okay. And the energy, so energy how to calculate? It is just, already we know power, it is a rate of change of energy, right? So now it is a reverse integration of that, we can say here. Already we know power P equal to V into I, right? Energy is nothing but what? So integral of power, right? So that is only here, integral of power, integral of P of tau d tau. That is nothing but what is P? V into I. In this way we can find energy. Okay, thank you.